Last video we saw that the speed of light in a medium is slower than the speed of light in a vacuum, and that has some effects on wavelengths of light as it traverses from one medium to another. Here we're going to take a look at a different phenomenon associated with the change of speed, and that's called refraction. So let's imagine that this is a surface here. We can do better. So let's imagine that's a surface here, and above the surface we have air, and below the surface we have glass. Let me go ahead and erect a normal again. So this is our normal, which is perpendicular to the surface. Okay, and let's say that we have a ray of light coming in, like so. This is our incident ray. And we already saw that we will have a ray that reflects out at the same angle. So here's our reflected ray. And its intensity is less than the incident ray. And I had also mentioned before that, doggone it, that some light will also propagate through into the medium, glass in this case. This gets called the refracted ray. And again, its intensity will be less than the incident ray as well. At least until we get to total internal reflection, but that's for a future video. Okay, one of the things that you'll notice here, the index of air is roughly 1. The index of glass, again, is roughly 4/3. So the speed of light is slower in the glass than it is in the air. And one of the things you'll notice here is that the refracted ray, so we'll call that theta 2, the refracted ray bent towards the normal. We'll call this angle here theta 1. So these two angles are not the same. So I'll do a single dash there, double dash there. General rule of thumb here is that if you are going into a higher index material, the light will bend towards the normal. And if you are going from a higher index to a lower index material, so if this were going the other way, the ray of light would bend away from the normal. Notice too that this refraction only happens at the boundary, so there's no like curving or hooking around or anything like that. It's just a flat out change of direction. And we'll see how that is when we get to applying Huygens principle to this. Anyway, it turns out that the angles are given by what's called Snell's law. It says that n1 sine theta 1 is equal to n2 sine theta 2. Okay. So let's see how that works out from a perspective of Huygens principle. So from Huygens principle, again, let's just imagine that we have an air and a glass interface. So here I'll drop a normal over here. There we go. And I will go ahead and bring in my incident ray. We'll make it blue. Okay. And we'll make my refracted ray light blue, just so we can tell them apart. Okay, so this angle here is our theta 2, and this angle here is our theta 1. Okay. Now remember, in the ray approximation, the rays are always perpendicular to the wave fronts in question. So let me go ahead and draw in the incident wave front. Oops. That looks pretty good. And that's perpendicular like that. And let's just see how this propagates. So at this instant right here, where this point is propagating out a wavelet that's going to move forward into the new medium, some point over here, let's say this point right here, will be propagating out a wavelet. Now let's take a look at the time it takes for the wavelet to make it to the medium. So the distance it will have traveled doing that will be v1 delta t, where delta t is just however long it took for the wavelet to propagate from here to there. And v1 is the speed of light in medium number 1. Okay, at that same time, the wavelet here would have traveled a shorter distance, say maybe this far. So this distance here, we'll say from here to here, we'll say is v2 delta t. Then finally, we can construct our new wavefront. It'll be from this point here to that point there. Okay. So let's go and take a look at this triangle right here. Oops. At this triangle right here, the pink one, and we'll compare that up against, yeah, here we go. And here we go, now that's too similar. Yeah, here we go. This red triangle right there. Now these are not similar triangles. However, if you go and take a look at this, you should be able to convince yourself that this angle here is also theta 1, and that this angle right here is also theta 2. Now the thing that the two triangles have in common is this shared hypotenuse right here. So we can write that the sine of theta 1, well, that would be the opposite over the hypotenuse, so that'll be v1 delta t over the hypotenuse. Divide that by sine theta 2, as long as we divide that by whatever that is, but that would be the opposite here, which is V2 delta t, also over the hypotenuse. The hypotenuses, the hypoteni, whatever, cancel, so do the delta t's. Okay, so this gives us that sine theta 1 over sine theta 2 is equal to v1 over v2, but we can write v1 as c over n1 and v2 as c over n2 by the definition of index of refraction. So we get 1 over 1 over. Rationalize the fraction, you get n2 over n1. And all that's left is to cross multiply. We get that n1 sine theta 1 equals n2 sine theta 2. And that completes the proof. Alrighty, so let's do a couple quick examples with this. So let's take a look first at, say, light going from air into crown glass. Now it turns out that there's multiple recipes for glass. There's what's called flint glass and there's crown glass, are the two most commonly used kinds of glass in optical glass making, although there are plenty of other recipes, trust me. But two of the most common are flint glass and crown glass. So air right here and crown glass right here. Air has an index of refraction of basically 1. This will be our n1. Crown glass has an index of refraction of roughly 1.523. And I say roughly because it does depend on the wavelength of the light, but that's for the next video series. And it doesn't depend on it very strongly. Okay, so let's say that we have light coming in. Oops. We have light coming in at an angle of 30 degrees. We would like to know what angle it makes going out. Now, we know it should be less than 30 degrees. Because again, with our rule of thumb that if you go from a low index to a high index, you bend toward the normal, our intuition will already tell us that we know that the answer is less than 30 degrees. So let's just go ahead and do it. All right, so we have n1 sine theta 1 equals n2 sine theta 2. All right, our goal is to get theta 2 by itself. So sine theta 2 will equal n1 over n2 sine theta 1. And then I need to take the arc sine of both sides. So theta 2 is the arc sine of n1 over n2 sine theta 1. Okay, so this will be the arc sine of index of refraction for air is basically 1, and for our crown glass is 1.523 sine 30. If you crunch that all through in your calculator, you'll get 19.2 degrees, which is indeed less than 30 degrees. So that's good. All right, now let's go back and do the same problem, except let's move that. There we go. Let's do the same problem, except instead of the slab of glass sitting in air, like we did before, we now have it sitting in carbon disulfide. By the way, I very much do not recommend doing this at home as an experiment. Just saying. Anyway, the index of refraction for carbon disulfide is 1.623. And crown glass is still 1.523. So once again, we will come in at our theta 1 equals 30-degree angle. But now, because we're going from a higher index to a lower index, this means that we will bend away from the normal. So it's going to look maybe something like that. So this is theta 2 equals, don't know yet. But the one thing that we do know, I can do a better question mark than that. But the thing we do know is that it's bigger than 30 degrees. Now, the nice thing about being in the habit of doing problems symbolically is sometimes you realize you literally just did it. If you look at this previous problem here, nothing changed except the value of n2. So if I did this all symbolically rather than sticking in numbers right away, this allows me to just plain copy and paste the result. Okay, so let's substitute in the new values. This will be the arc sine of 1.623 over 1.523 times the sine of 30 degrees. And again, if you run the numbers through, you get 32.2 degrees, which is indeed bigger than 30 degrees, and so that's what we were hoping for. Now, you may look at this and say, wait a minute, I know that the sine of an angle can run anywhere from 0 to 1 if we're in the first quadrant, and we always are. And if n2 is bigger than n1, that means that we could potentially be taking the arc sine of a number bigger than 1. And if I put in the arc sine of some number bigger than 1 into my calculator, I get various, depending on the manufacturer, I get various answers that all basically amount to the thing saying tilt. So what happens there? Did physics just break down or what? And I'll say there, hold on tight until the next video series. We'll see that when you get nonsensical situations like that, the intensity of the refracted ray would be 0, and the light purely reflects off the surface. This is what gets called total internal reflection, and I submit that this phenomenon is one of the single largest drivers of 21st century culture. But more on that in the next series. I thought I would finish this one up by doing another fun application. Let's say you are sitting in a boat. So here's some water. Here's your boat. There's you sitting in the boat, very happy about it all. Okay, and let's say you, sitting in your boat, you look in the water and you see a little fishy. I can do a better job of drawing a fish than that. Yeah. There we go. So here's our fishy. Now, anyone who's ever looked at a fish in water will remember that it seems like that if you look at the fish in the water, the fish doesn't ever seem to be at the depth the fish is actually at. It always looks like they're sitting higher than that. And why is that? Well, let's look at one point off of the fish and see if we can get some clue on that. If I look at, say, this ray of, if I look at this ray of light coming off the head of the fish here, let's say, it just shoots straight out. Oops, try that one more time. There we go. The angle of incidence is 0. In the case of the angle of incidence being 0, the angle of refraction is also 0. So that ray will continue to shoot straight out. But this ray here, let's say, it will bend away from the normal, like so. This is greatly exaggerated. Let's do a little better job of that. It'll bend away from the normal, like so. Okay. Now if we track back where these rays seem to be originating from, okay, this one just goes straight back. But if I look here, it seems like this ray here is originating, oops, at the head of the fish. So if you were to look down from above and look at the fish, the light would all be seeming to be coming away from a point a little higher up. So this is a virtual image. So we can say here that this is my object distance, DO, and this is my image distance here, DI. And since this is a virtual image, I can't form it on a screen, this will be negative for a positive object distance. I'll dispense with the actual calculation here, but as long as you're not looking too obliquely at the fish, if you're looking reasonably straight down from above the fish, you can show that the image distance is roughly equal to minus, again because it's a virtual image, n2 over n1 times DO. Sorry, n1 over n2. Times DO. So in the case of water, the index of refraction of water is about 4/3. So then this is minus, air is, oops, sorry, this is n2 over n1. n2 over n1 DO. But we have to be very careful. The first medium the water is in is here. The second medium is here. So we're going from medium 1 to medium 2, as always. So anyway, this is water. Medium 2 here is air. So this will be 1. Medium 1 is water, which is 4/3 DO, be minus 3/4 DO. So all the distances that you see when you're looking underwater, from air into water, so same deal if you've got swimming goggles or a diving mask on, something like that, all the distances seem to be about 3/4 of what they actually are. And with that, I will catch you on the next one.